We spent practically the whole class period analyzing just one single problem. The problem said, well, the object accelerates from 10 to 20 meters per second in a 5-second time interval, and we want to calculate all the quantities we can, assuming uniformly accelerated motion, meaning we have a straight line velocity versus time graph. I wrote the basic triangles up here that govern this situation. A definition of average velocity leads us to a triangle where delta S, delta T, and V bar are connected, and we know how to use the definition to see exactly what that connection is. Definition of average acceleration, again, involves change in velocity, change in time, and average acceleration in a relationship that comes again out of the definition. Definition here being average velocity is the average rate of change of position with respect to clock time. Average acceleration is the average rate of change of velocity with respect to clock time. Very similar definitions, just one word that's different in both. One word that's the difference between the two. We use position here, velocity here, rate of change of position, rate of change of velocity. I think everybody's pretty conversant with that because everybody's doing pretty well with this. Okay, and then our straight line graph gives us a straightforward relationship between V naught, VF, and average velocity V bar. So there are two ways to calculate an average velocity if we know the acceleration is uniform. One is, it turns out to be you divide delta S by delta T, and again, you should know how to use the definition, the verbal definition, to get to that relationship. And here the straight line graph tells us that the initial quantity, or the average quantity, has to be the average of the initial and final quantities. So we just average V naught and VF to get V bar. And then I put this in, it's not really necessary. It's a definition of delta. It just tells us that if we know V naught and VF, we get delta V. And subtract V naught from VF. That's the meaning of delta. So it's not really part of our definition of uniformly accelerated motion. But we include it here just as a reminder in case we happen to get a little bit confused or lost. At some point, you just really probably stop writing this one down, but you probably need these as a reminder until you've done a good number of problems. Okay, so initial velocity is easily identified to be 10 meters per second, final velocity 20, delta T 2 seconds. People have proven to be quite good at identifying initial velocity, final velocity, change in clock time or time interval, change in position, delta S, and acceleration. The one thing I'll say is that some people are mixing up delta T and delta S. Common sense tells you that this can't be delta S because you don't measure a displacement in seconds, and you would not say that 14 meters is a delta T. It's not a time interval, it's a displacement, a distance interval if you wish. Okay, well, having noted that we know V naught, VF, and delta T, we write down V naught, VF, and delta T and start asking ourselves, what can we determine? Well, if we know V naught and VF, we know that we can find delta V. I mean, that's just one of our triangles up here. This triangle up here, okay? So V naught, VF gives us delta V. That's very obvious. We should, as soon as we see that we know V naught and VF, we know that we can find delta T, and also, assuming uniform acceleration, so we have the straight line V versus T graph, we can average the two to get the average velocity. So these are very easy to obtain. Now, we could list our 10 quantities, V naught, VF, delta T, V bar, delta V. What are the other two? A and delta S. Now, I wrote A and delta S as question marks before I filled in the rest of this diagram. Okay, so at this point, having observed that we can find delta V and V bar, we ask ourselves, okay, what's left? And it's going to be A and delta S. So here I've listed the quantities that weren't given, the V bar, the delta V, the A, and the delta S. I've checked off V bar and delta V because we've seen how to get those. How would we get A? Well, what is acceleration? See, average rate of change of velocity with respect to clock time. That means it's going to be change in velocity divided by change in clock time, delta V divided by delta T. And with that reasoning, we see that knowing delta V and delta T, we can find the average acceleration, and we can drop the bar over the acceleration if we have straight line velocity versus time graph, because that makes the acceleration uniform. Okay, well, we know that. We need to know that. We need to invoke that. But then we can see easily that, okay, we got delta V and delta T, we can find A. And what's left? Delta S. Well, go back to the definition of velocity. Delta S, delta T, and average velocity are connected in such a way that if we know two, we can find the third. So delta T and V bar is going to give us delta S. At this point, we don't have to have done any calculations. We simply see how everything works together to give us the flow of the problem. Okay? Now, we go ahead and fill in how we calculate these things. Delta V is VF minus V naught. Okay? V bar is the average of the final and initial velocity. It's not VF plus V naught over delta T. It's not VF plus V naught minus V naught over 2. You would never remember all those formulas correctly unless you have very good visual memory. You have to understand what the formulas mean so you don't confuse them, because it's very easy to put a delta T down here or a minus up here or even both. That'd be a disaster. Okay? And what's the common sense? You just have to know the common sense of this reasoning. If you have a straight line graph, you can average the two velocities to get your average velocity. And that's what we do. Now, just talking about the relationships, it's really easy to fill in the numbers. Okay, so how do we get acceleration? Well, that's pretty straightforward. If we start with the definition, rate of change of velocity with respect to clock time, we go through one step, change in velocity divided by change in clock time, and we can write this down. So there's the relationship for acceleration. And what about delta S? Well, we know that V bar is delta S over delta T. Again, we start from the definition, rate of change of position with respect to clock time. Gives us change in position with respect to clock time. That's how we get the average velocity. And then we just rearrange this. But this is really almost common sense. If we know the average how fast we're going and how long it is, we pretty much know to multiply the two. We do want to go back to our reasoning, though, to double check it and make sure we've got it right so we don't do something unfortunate and get a wrong result. Okay. Well, now, knowing what the relationships are, we can calculate delta V, which is the change in velocity. We subtract the initial from the final, we get the change. Calculate the average. We go from 10 to 20 meters per second, average those two, we're going to get 15 meters per second. We can do delta V over delta T now that we've gotten delta V, using the 10 meter per second delta V that we got here, divided by the 5-second delta T, and we get 2 meters per second squared, our acceleration. And now we get delta S, again very easily. We've calculated delta V bar. See how easy it is to say the wrong thing, or even write down the wrong thing, or even get the equation wrong? Okay, so we know V bar, and we multiply that by delta T. 15 meters per second multiplied by the given delta T, 5 seconds gives us 75 meter displacement, and there we have it. And we've reasoned it out in a way that makes sense. At every step, we can make sense of what we've done. If we've done something wrong, we can figure it out, and we gain intuition about what these things mean, so that with a little practice, all this becomes just a very straightforward reasoning process that we can pretty much work out in our heads. That doesn't mean that using the equations, which I've written here, is an irrelevant skill. It's a separate skill. You can use the equations just by identifying V naught, VF, and delta T, and doing a mechanical plug-in process without ever having to think about how anything is related or what anything means. Okay, you can do that, which is why I don't start with the equations. I want you to understand the relationships. I want you to understand the scheme. I want you to completely understand uniformly accelerated motion as opposed to just making it a mathematical exercise. Now, of course, many people get great results teaching this subject this way, and they actually get good intuitive results by posing the right kinds of problems and asking the right kinds of questions, all of which students are going to avoid if they can just get the right answer using the equations without doing any thinking. Much easier. That doesn't build what we need. That does not build the kind of thinking and the kind of skills we need to successfully do physics. At least my opinion is that it doesn't. My opinion hasn't been thoroughly researched, and nobody in their right mind is going to devote their graduate school career to researching it. But I'm pretty well convinced of this. And what I get from my students who've been successful, of course I don't hear from the ones that haven't been. What I get from my successful students is that this sort of thinking is extremely valuable. Takes you out of the circle the right number on the SOL mentality and gets you into thinking about reality, about the physics, about what's going on in front of you. There are other ways to approach it, and I have no quarrel, but this is the way I choose.